So I want to talk about today about the so-called non-causality problem in non-local extensions of DMFT and what kind of implications this has for high-energy satellites, for example, in the electronic spectral function of correlated electromaterials. So this was work which was done when I was working in the group of Silke Biermann together with Hong Jiang from Peking University and Jae-Hoon Sim, who at that time also was at École Polytechnique. Okay, let's get started. Of course, I think everybody is well familiar with the DMFT method. I mean, we use the DMFT method to approximate the electronic correlations to be local in order to introduce correlations via a local self-energy, which is frequency dependent. So then we can get an approximation to the true lattice Green's function via the Dyson equation, which has correlations included within this local self-energy. So I want to look at the case where we go beyond that DMFT approximation and reintroduce non-local correlations. Of course, there has been a lot of work already done in that direction since the beginning of DMFT, like cluster approaches, diagrammatic expansions around the DMFT solutions, perturbative approaches like GW plus eDMFT, self-energy embeddings, and so on. And I want to look at the case where we essentially extend the local self-energy to include some kind of momentum dependence. And I want to talk about the problems that we encountered during these investigations. So also, of course, we were not the first ones, and it has been since the beginning of introducing non-local correlations to DMFT, something in that direction has been reported. So recently, in the recent years, it re-emerged in the case or in the context of GW plus DMFT. And what has been discovered at that time was that there is something which has been called at the time causality violation. And it was discovered that, especially in the strong quality regime, this causality violation seriously impacts the prospects of using this kind of non-local extension of DMFT. So what they mean in this case by non-causality is negative spectral weight in the diagonal element of any physically relevant quantity. This could be, for example, the Green's function or the spectral function. So this means, for example, here, this could be some spectral property. Here it's a hybridization function, but it could be the electronic spectral function, which should be purely positive, but if it develops some kind of negative weight, this is what we call non-causality in that context. And this is what has been reported by the previous papers. There have been many other papers which also talk about this problem. And for example, it's also been reported in the frequency-dependent interactions, which is a component in this kind of calculations. It has been conjectured that it's not a specific feature, but any method that includes dynamic long-range polarizations is bound to yield this kind of non-causal on effects. In general, also then this went hand in hand with a reduced electronic correlation strength. So this was found, for example, substantially reduced effective local Coulomb repulsion when this emerged, these kind of non-causal features. Also in cluster extensions, like for example, the dynamical cluster approximations, non-causal features has been reported, and also this led to a more metallic and less correlated solution in general. And as well, for example, also in dual fermion approaches, in this paper, there was no reports about non-causality, but also when these non-local correlations were included in the full consistency loop, that also the system became less correlated than before. So we also discovered this kind of problem in our calculation, so we tried to look into this a little bit more in detail. And what we found actually that this problem emerges quite naturally from the following condition. Because in the beginning, of course, we were wondering why does this happen? Because in general, we solve the DMFT, the effective impurity problem exactly, for example, with continuous time quantum Monte Carlo. But in fact, this non-causality problem comes from the self-consistency condition that we try to reproduce the local Green's function by the Green's function of an impurity reference model. And this can be seen very quickly from, for example, considering the exact solution of a dimer problem. So what I want to consider here is shown on the left. We have a dimer system, local interaction on each side, a hopping between the two sides. And then what we want to do is we want to solve if we want to apply a DMFT calculation to this problem, which means we map the system onto one impurity site and we have one bath site attached. And since the system is very small, we can solve it exactly. This is the non-local Hamiltonian, which includes the hopping between the left and right side. And now assume that we know the self-energy, which we can get from exactization, for example. We can generate the exact Green's function for the full dimer. And then we can apply this general DMFT approach. We map this Green's function onto the one side, which means we just take one diagonal element. We calculate the effective impurity problem from the exact solution, and we can evaluate it analytically, which is this result here on the bottom. And one can quickly confirm that if the self-energy between the two sides, so the non-local one, which cannot be generated by just a local reference system, if this is non-zero or has a frequency-dependent imaginary part, in general, this quantity will develop non-causal features such as negative spectral weight. And this is here an illustration, numerical illustration of that problem. So what is shown here is, okay, in this case, it's the Barth-Green's function. On the left, this is the full complex plane. X is the real part of the variable and Y is the imaginary part. And here on the right side is the projections on the real frequency axis of the spectral function. And the lower one is on the Matsubara function, Matsubara axis. So this lower right figure is along the y-axis for x equals 0, and this data here on the top is along the x-axis for y equals 0. And now if you look at this quantity for small interactions, it looks like this. We actually find that the Barth calculated from the exact solution of the dimer has some very small negative peaks. So this is what we would consider as non-causal weight. On the imaginary frequency axis, so far everything looks fine. So now if we increase the interaction, actually some poles detach from the real axis and move into the complex plane. Then here this gives a more complicated frequency dependence and larger non-causal weight. Still on the imaginary Matsubara axis, everything looks not suspicious. If we increase it even more, the poles move even further away from the real frequency axis. At some part actually it seems to improve on the real frequency axis, but this is just because the poles actually move away, so we don't see them. And interestingly, so there's no any peculiar or special feature visible on the Matsubara frequency axis when this kind of detachment of the poles from the real frequency axis happens. So we try to look into that, where does it come from and how can we solve that problem? And this can be very simply done in a short calculation by revisiting, for example, one possibility to derive DMFT, which is, for example, here the cavity construction. And in the cavity construction, let me just repeat the main ideas. What we do is we start with writing down the general lattice action, for example, here for a lattice here, and we separate into three parts. This whole summation of the lattice action, we take the local action on a given site, which we have separated here, the part which connects the site to the remaining lattice, which is delta S, and then the remaining lattice is S0. We integrate out all the other degrees of freedom. We obtain a kind of perturbative expansion of the local component of the lattice action and some correction here, which this is the first approximation that we will then do. In the limit of infinite lattice connectivity, as has been shown, of course, this reduces to this kind of equation. We have the local part plus some correction in the part of the action which connects the local site with the remaining part of the lattice. All the other terms vanish when we have for infinite lattice connectivity. If we concentrate on the finite dimensional cases, as we usually have, this constitutes the first approximation. Then we can evaluate this part, and it looks indeed like a impurity action where we have here the so-called Barth-Green's function, which is given as frequency, chemical potential, and the Green's function for the lattice with the zero side removed. And if we apply a second approximation, which is only correct in infinite connectivity limit, we can map this back or find a connection back to the original lattice, where here we have the Green's function of the original lattice connecting sides ij and I to 0 and so on. This then allows us to close the self-consistency loop. So for now we have applied 2 approximations within these steps. Then in general what we do is we apply a third approximation, which is assuming that the self-energy is local. But if we just skip this step, in a very simple calculation, actually one can evaluate this last equation to yield a slightly more complicated form that we usually use in DMFT, which evaluates to, we have the usual part of this local Dyson-like equation, and then some correction-like term, which is essentially a local projection of self-energy times Green's function terms. And we can very quickly confirm that, for example, when the self-energy is indeed local, this whole term vanishes and we recover the original DMFT self-consistency equation. So this would then constitute the third approximation. If we just skip this step, we are left with this kind of correction term. So, and the same can actually be done also when we go a step beyond and also extended two-particle quantities, such as in Hubbard, DMFT, and so on. So also this derivation can be extended within the cavity constructions to non-local interactions, for example, and then also it recovers the usual Dyson-like form with some kind of correction term. And interestingly, what we can see is we have found that, so this quantity, the Green's function, develops non-causal features, but actually one can confirm that here this upper equation, including the 2 approximations that we have done before, which are valid in the infinite connectivity lattice, this constitutes still a causal Green's function-like form. But we have seen, for example, for the dimer, if we take the usual self-consistency form for DMFT, this then creates a non-causal feature. So which means that this missing correction term is the one which is responsible for the non-causality features. And if it is included indeed, then this is just an exact rewriting of this upper equation. So there's no additional approximation involved. If we approximate the self-energy to be local, we recover the original DMFT form. But the thing is, if we now include a non-local self-energy in our self-consistency scheme, using the standard self-consistency scheme will create the non-causal features, because this term, which is non-zero if the self-energy is non-local, in principle should be included in my opinion. And this can be quickly analyzed. For example, if we revisit now the dimer, the general DMFT self-consistency scheme we evaluated to this result, where the hopping was renormalized by the intersite self-energy. If we include this corrective term, we recover a simpler form, which is actually only the bare hopping between the site of the impurity and the rest. And this kind of makes sense because in the original derivation we see that here the Green's function of the remaining lattice is coupled via the bare hoppings to the impurity. Here actually we can see that this is not the case because the hopping is renormalized by the intersite self-energy, but if we include this correction term, it's just the bare hoppings. So this is consistent with the original lattice with cavity construction. So let's see what happens if we now include this in a full DMFT, full self-consistent non-local self-energy calculation using the exact non-local self-energy from the dimer. So what we do is we solve the impurity model, now including the exact non-local part of the self-energy from ED of the dimer, and we iterate on the local part of the self-energy by solving the impurity model with an exact diagonalization on the real frequency axis. Of course, since we want to compare to the original formulation, the non-causal features correspond to a non-Hermitian impurity Hamiltonian, so the ED formalism has to be a little bit generalized. But if we do this, we actually find an interesting result. If we perform a standard DMFT calculation, we recover that we have non-causal features. Here in the red graph is the spectral function performing the self-consistency in the usual scheme without the correction term. The blue one is the one including this correction term compared to the exact local part of this spectral function of the dimer. If we increase the interaction, then actually we see that the standard Dyson-like equation, so the original formulation here we call Dyson, actually fails completely and obtains something like a non-normalized spectral function. And including this correction term, actually, it seems it's in qualitative agreement with the exact solution. It still has Hubbard-like peaks and real normalized bonding-antibonding splitting, which is not perfectly reproduced, but it obtains a rather reasonable result compared to the exact one. And this is interesting in how the general scheme fails, because we've seen that the metadata data shows no problematic behavior in general. And this is actually related to the fact that, as we've seen before, some poles detach from the real axis. And this means that the usual Cauchy integral equation that we use to connect real frequency data to the Matsuberry data, for example, using also for analytic continuation, this is no longer valid because this only works if you have poles only situated on the real axis, which means we cannot interpret our data on the real axis based on the data that we have on the Matsuberry axis. And this can be seen by looking, for example, very clearly here on the self-energy. So this is the identical calculation as on the previous slide. We have solved the dimer in the self-consistency scheme, including and not including the correction term. For strong interactions, the original formulation without the correction term actually fails, and what we can see is the self-energy somehow seems to be almost vanish on the real frequency axis, while it has some rather large imaginary part on the imaginary axis. And this is very unfamiliar, but it's just a result that there's no correspondence anymore from the Cauchy integral equation between the real and the imaginary data, which of course is a problem in practice. Just as a side note, so also this result can be extended to cluster methods. So for example, in the papers that I've shown before, it was discovered that also non-causality can emerge in the cluster extensions. For example, if we perform cluster DMFT calculations, let's assume we do a two-dimensional Hubbard lattice. For example, we create a 2x2 cluster, we calculate the non-local short-range interactions in the cluster, which means the nearest neighbor self-energy. And what can be done is, of course, we can do a kind of reperiodization of the self-energy, because this kind of non-local self-energy should also be the one connecting different clusters. So if we reperiodize the self-energy, this then creates an effective momentum-dependent self-energy. And then it has the same effect, because now the self-energy is momentum-dependent, it's included in the impurity model. This in general can create non-causality features. So also this will give rise to a non-zero correction term that we've seen before. The same or similar thing happens in the dynamical cluster approximation, where the self-energy is approximated to be constant on certain momentum patches in the Brillouin zone. If we now take this momentum patches of the self-energy and interpolate it with a smooth function in K-space, on each of the patches, the self-energy now acquires a momentum dependence. So in total, also this is a momentum-dependent self-energy. This can create a non-causal feature, so this is also the origin of the non-causal features that have been reported before. So also then in this case, the correction term is non-zero and can be included. And we've just done a very, very simple comparative calculation. Of course, it should be more elaborate to do some real benchmarking, but what we've done is we have looked at available diagrammatic Monte Carlo data for a weakly correlated system. This is a two-dimensional Hubbard model for 20% hole doping away from half filling at rather high temperature for U = 4 times the hopping. And what is shown here is left cluster DMFT approach, right dynamical cluster approach, including and excluding this correction term. The black data points is diagrammatic Monte Carlo, which can be considered converged. And green data is the standard cluster DMFT approach without any repolarization of the self-energy or without any interpolation. And here I show the real part, because actually this in the imaginary part there's not much difference. It agrees rather well. The red line is the calculation reperiodizing the self-energy. The blue line is the one where we include then the correction term. So the red one in general can be non-causal, the blue one fixes the non-causality. And what we can see is actually including the non-locality of the self-energy in the standard formulation moves the real part of the self-energy further away from the probably exact solution, while including the correction term in the self-consistency brings it closer to the exact solution, and this happens in both cluster DMFT and DCA approaches. So it seems to push the self-consistency in the right direction in this case for this simple calculation. So let's come back to some real materials. I want to talk about some transition metal oxides. And here, for example, for the system of strontium molybdate, which has been considered before in experimental and theoretical investigations, it's quite interesting because it's a very low resistivity material, 5 microohms centimeter at room temperature, which is pretty low. And it's interestingly because also transparent conducting material, and compared, for example, to the well-studied strontium vanadate material, this is a 4D 2 materials, more extended d orbitals and 1 electron more compared to this reference material. So it's assumed in general to be less correlated to strontium vanadate. And this gave rise to some discussions because in the experiment here, for example, for photo emission, it has a renormalized quasi-particle like feature around the Fermi level and some kind of broad shoulder-like feature in the occupied part of the spectrum. And this part was up to some discussion whether this could be, for example, plasmonic excitations or Hubbard band, because, of course, as expected, density functional theory approaches do not reproduce this feature as in strontium vanadate, but DMFT also does not produce a clear shoulder-like feature. So this led to the initial suggestions that indeed this could be a plasmonic feature. Then GW DMFT calculations, including electronic screening and non-local correlations, have been done, and actually it has been found that the system appeared much weaker correlated than standard DMFT calculations. So also it was suggested that this could be then a plasmonic feature because local correlations seem to be too weak to induce Hubbard bands. But the thing is, this was of course done with the old formulation of the non-local DMFT extensions. During that time, of course, also different experimental results came out, so they all differ in some kind of aspects. Of course, different thin films were utilized, also biostructures, which all gave rise to different spectral results. In some parts it was proposed that, for example, at the surface, correlations tend to be stronger, so there could be both lower Hubbard band and plasmonic features. In the bulk, maybe we only have plasmonic features. So also this, of course, then raises the question, can we somehow distinguish plasmonic effects from Hubbard correlation satellites in these kind of materials? And I just want to talk very quickly about what is the difference between the two, or how we at least define the difference between the two. We have now two features in the spectral function, Hubbard satellites and plasmon satellites, and we can define them, I think, kind of clearly in approaches such as GW plus DMFT. So what do we do in this case? We have non-local interactions in the real material, and in approaches like extended DMFT, we can downfold them into an effective frequency dependence of the local interaction. An approximate form of this local interaction is shown here on the left in this graph. Upper part real and lower part something like the imaginary part of this interaction. They all have qualitative features that at low frequencies here on the left, they recover a low screened value of the Baer-Kundab interaction, around 3 eV for these materials. At high frequencies, where electronic screening is less efficient, it recovers the Baer interaction. And there's a transition at the main plasma frequency of the electronic system down to the low energies. And in general, in a standard DMFT calculation, we use the low energy screened value. But if we do extensions such as eDMFT, we can include this full screened frequency dependence. And what we can see here is in the frequency dependence, we have certain plasmonic excitations corresponding to the main plasma excitations, but also subplasmon excitations, for example, from the T2G manifold in these kind of systems. And we see that around 3, 4, 5 eV, we have this kind of excitations, which then in general induce also plasmon satellites in the spectral function. So we see that, at least in these systems, plasmonic energies and Hubbard satellite energies are rather of the same order of magnitude, so we can expect these two features emerge at the same energy scale. So let's find a way of distinguishing them, and we propose.
Sorry to interrupt
yes.
with a quick question. This is
Sure.
for Strontium number 3, the curves you're showing.
This is in fact strontium vanadate, what I'm showing, but strontium
Okay.
molybdate almost looks the same with just slightly reduced interactions because it's 4D. But it looks surprisingly similar. So what we propose is, because in general what we include in DMFT is the local frequency value. So at 0 frequency, the instantaneous interaction is the one which includes the local atomic-like physics, the local atomic multiplet features. So this gives rise to the Hubbard bands. The frequency dependence is the one which gives rise to the plasmonic satellites. So what we can do is, if we keep the frequency dependence, we approximately keep the plasmonic satellites. But if we shift, for example, the low frequency value to 0, this will completely remove the Hubbard bands. So we have one way of removing the Hubbard satellites, so the ones induced from a local instantaneous interaction, and keep only the ones which come from collective excitations of the electron gas, which are encoded in the frequency dependence. So this is what we propose as a way of distinguishing these two features. And we did a very simple check on the one orbital Hubbard-Holstein model and found that it seems to work rather nicely. Here on the left is the spectral function of a beta lattice for the Hubbard-Holstein model. We see that we have plasmonic excitations around the coupling to the plasmonic modes around 5 eV. We have multitudes of multiple replicas of these plasmonic excitations, and they are almost unaffected once we reduce the 0 frequency part of the interaction, while the Hubbard band here around 1 to 2 eV vanishes completely and the quasi-particle peak is restored. And this is even more visible here in the imaginary part of the self-energy, where we have the three, like a peak-like structure. The first one, which gives rise to the Hubbard bands, completely vanishes once we shift the interaction and the 0 frequency value down to 0, while the plasmonic, the features which create the plasmons are almost unaffected. And okay, in the interest of time, maybe let me skip the part where we applied to strontium vanadate, because it's actually quite similar to strontium molybdate. So let me immediately go to this system. What we actually find is that when we apply this scheme of reducing the interaction to 0 at the 0 frequency part, we see that indeed different satellites behave differently. So here on the left, this is the full spectral function. The black line is the density functional theory result, which does not recover the Schoelter feature. Here on the upper right, this is zoomed in result. What we see is that around 5 electron volts, we have in the occupied part, we have a plasmonic-like excitation, which is completely unaffected by changing the static part of the interaction. We have here the shoulder-like feature, which is drastically reduced when reducing the interaction. And in the unoccupied part, actually, we have something like 30% remaining of the original peak. So within our interpretation, this means that the feature at plus minus 5 eV in the spectral function, we identify it as a plasmonic excitation. The shoulder-like feature is a majority composed of what we would call a Hubbard satellite-induced interaction, and actually, we have an overlap of the two features in the unoccupied part of the spectral function, which is composed of roughly 70-30% of Hubbard-like and plasmonic-like features in the spectral function. So finally, let's compare to experimental data which is available. What we show here is the dots correspond to different experimental samples and experimental data from photo emission. The black continuous line is our calculation, including the correction term in the self-consistency. The orange line is published data of the original formulation from DMFT. And what you can see is, of course, it's difficult to compare the shoulder feature. What seems to be rather consistent is, for example, here the width of the quasi-particle like excitation which seems to agree rather well qualitatively with our black line result. In the standard formulation of GWDMFT, the quasi-particle width is actually much larger, which seems to be agree not so well with the experiment. And also the shoulder-like feature is strongly suppressed. Of course, the shoulder feature varies quite a lot in the experiment, but if we observe the same trend as has been reported before, including the correction term, which removes the non-causal features, also retains the strength of correlations. Not including this term induces non-causality features, which then reduces the correlation strength. So this increase of the quasi-particle width is, I think, indeed due to the non-causality features in the self-consistency scheme. So since we cannot say that much about the shoulder feature, but especially for the quasi-particle width, I think this indeed indicates that this material is more strongly correlated than what has been suggested before by the GWDMFT calculations, and is rather similar to actually what obtains DMFT, but here in this case we can actually also distinguish the two features, and we think that this is also majority Hubbard-like and not plasma-like excitation. Okay, and with this, I'm at the end of my talk, because I think I've run out of time, so maybe I will just leave it like this and show my conclusion. I want to thank you very much for your attention, and I'm happy to answer any questions. Thank you very much.
Olivier, Jean-Gras, you want each other questions?
Yes, sure. Thank you very much, Steffen, for the very nice talk. So we're ready to take some questions. So please raise your hands if you have any questions. I see that Andy has a question first.
Hi, sorry. Correctly. Can you hear?
We cannot hear you, Andy.
You cannot,
Can you
Andy,
repeat?
we have a sound problem.
Can you repeat?
if you want, you
All
can
right,
write it.
is this better?
Oh,
Yes,
yes.
now it's better.
Yeah. Okay, all right. Thank you. It's just for, okay. Good. So back in the Stone Ages, we found that quote causality violations in some of the cluster DMFT methods could be viewed
yes.
as closely analogous to the ringing phenomenon in Fourier transform. You know, if I make a Fourier transform of a step, it overshoots.
Yes.
So what you're saying here is not exactly that, but is there some similarity? And in particular, you know, would it, for example, these things go away as I get reduced in amplitude as I go to bigger and bigger clusters?
I think this ringing problem is very different from what we discussed here. Of course, also what the same thing will happen if we go to larger and larger clusters. The self-energy that the momentum dependence of the self-energy, of the non-local self-energy, which is outside of the cluster, of course gets smaller and smaller. So also these features, the non-causality and these problems will go away because we treat more and more of the non-locality in the cluster itself. So then the problem is also reduced, because if the non-local part which goes outside of the cluster is the problem, all non-locality inside the cluster is of course just an off-diagonal element, and this does not create problems. So if the larger cluster gets larger, the problem will get less, but it's disconnected from this kind of ringing problem.
Yeah, I wasn't saying it was exactly the same, but I wonder if there is still some kind of analogy. But all right, thank you very much. Sorry.
Interesting.
Next, we have Antoine.
Yes, thank you, Stefan. This is a very interesting and stimulating talk. I have a question about starting with the simple dimer model that you explained at the beginning. So also in somewhat the Stone Ages, there was a very nice paper by Olivier Parcollet, Giulio Biroli, and Gabi, which actually investigated the mathematical conditions for non-causality in terms of the so-called Kutkowski rules and all that stuff. And what they found at this time is that the non-locality doesn't show up immediately for arbitrarily small, if I remember correctly, sigma non-local. But, if you were to put a coefficient alpha in front of the non-local part, that it would appear for a critical value of this alpha, if I remember correctly. In contrast, you seem to say that in this simple dimer case, it appears for arbitrarily small non-local sigma. Is that correct?
Yes, this is indeed correct. So, looking at the analytic equations, actually, we see that for arbitrary small interactions, the impurity quantities become non-causal. And please correct me if that's not correct, but I think in this paper, non-causality was defined as the imaginary part of the Metzeler data becoming or changing sign. And indeed, there's a critical value for this. If we look at the real frequency value, this happens for any finite value. But for the
Not
Metzeler
really.
data,
I mean, the original argument is in Kutkowski rule, that's Kalish, but we can discuss separately the technical detail.
okay.
I think it's
No,
because we
I
are not
do- I
talking
do
about,
think
you are
this
not talking
was
about
the-
exactly the same problem here. We are talking
Oh,
about
really?
representing a dimer with a delta or directly a full DMFT cluster calculations, but okay, we can discuss more soon. It's a technical point. Sasha.
Yes, Sasha Lichtenstein.
So I cannot hear you.
We can't hear you, Sasha,
Sasha.
for some reason. We have a problem today.
Maybe we can take the next one and go back to Sasha.
Yeah, yes, we will.
Now you can.
Take it. Try again.
Yes, now?
Yeah, this is good. Okay.
Okay, great. Great. Thank you, Steffen. So you see, I just want to say that 20 years ago, even with Antoine and Misha Kuznetsov, remember we did this two-side cluster test, and I was guilty to not finishing this. And Misha wrote this cavity construction for two-side cluster. Probably it's the same as now Steffen and Silke is doing. And I see that it's overcome, of course, causality problem, but still expression is so, not nice, I would say. And later, yeah, it's exactly this in square, this expression.
It's not nice.
Yes, but my question is that later with dual perturbation, we understand how exactly solve this problem of disentangle local and non-local contribution. Did you think ever how it's related? So probably we all need to think, because it's clear that you start from not weakly. So if you start already from DMFT doing beyond, yeah, it's a strongly strongly correlated perturbation. So yeah, so you're not supposed to add two self-energy, local and non-local. That's what dual theory said. Of course, it's it's much more elegant way of solving this problem. And I have feelings that it's, in some sense, it's equivalent what this causal solution of U is. Have you ever seen it?
Yeah, this is a very interesting question. And when I discussed with Zhenya Stepanov in Polytechnique, we quickly tried. Unfortunately, we didn't go very far in that time because somehow we lost track. But we looked at the two different self-consistency conditions from dual fermion. And the one requiring the local Green's function being the impurity Green's function is, of course, recovers the standard result with non-causality. The second self-consistency condition, I think, where we require that this non-local contribution to the local part vanishes. It's different, but for some reason, it looks very, very similar to this correction term. So I looked at some kind of numerical forms of the impurity model, and it looked very similar. it
Mhm.
didn't fully remove the non-causal features, but it strongly suppressed them and it looked very similar. So for some reason, which I don't really understand,
Mhm.
it seems to be very, very similar to this correction term, but it's still
Okay.
different.
Okay, thank you. No, maybe we still need to finish this with Misha is here.
So I think this would be very interesting, but
Yeah.
at that point also we didn't go further than this, unfortunately.
Yeah. It's my fault that I didn't finish this 20 years ago. Okay, thanks, Alan.
Okay, next, Eric.
Yes, thank you for the nice talk. My question was about the Matsubara data that you show. So what
yes.
you're pointing out is that you frequently have Matsubara data that doesn't become positive, so that you don't explicitly see non-causality. But
Yes.
now with these Nev van Lina papers by Emmanuel from and the Michigan group, they provide kind of stronger conditions on what it means for Matsubara Green's function data to be causal or not.
Yes.
So there are certain sums that should be positive, I suppose. If you look at the data here, do you see the non-causality if you look at those sums? So these, I think they were called PIC conditions or something like this.
Okay, I don't fully remember what they did, but I think also they did something similar as looking at the transformation for imaginary time. If you look at I think even more odd order derivatives, indeed it can be seen that, for example, then the curvature changes sign or something. So it can be identified, but I think when we investigated this, it's not a sufficient condition. So if we find something strange, for example, in the curvature or even order derivatives, then for sure it's non-causal, but it's not necessary that if we don't find anything that the data is causal. So this is at least my understanding for now. There is unfortunately not a good identifier which clearly tells you, okay, this data is fine and causal, and this one is not, by only looking at the imaginary data, imaginary Matsubara data.
Okay, because my impression was that the rules there for these Nev van Lina functions were really to show that the function has the proper analytical structure in the entire upper half plane. So
yes, I mean, of course, in this analytic continuation approach, what we would like to do is we construct functions on the Matsubara data that then have a real have a causal part on the real axis. What we are faced with in practice is we do our calculation with CTQMC, we obtain some Matsubara data, which might already be non-causal. So actually performing analytic continuation, even with Nev van Lina, doesn't make sense because we don't have, where is it? We don't have the connection anymore between the Matsubara and the real frequency data. So even if we find a good representation with Nev van Lina functions to our bare CTQMC data, the result, in my mathematical understanding, is useless because it does not correspond to the actual real frequency data, because this connection is lost. In this analytic continuation, we want to go the way backwards. We assume that, of course, the data is causal, and then let's find something which is constructed from a causal set of functions. To my understanding.